Good morning. We are going to continue our class of earthquakes. So, we are going to be talking and learning a little bit more about how they are formed and what is going on. So, you may remember that we already talked about the causes of an earthquake, okay? It was by the sudden slip on a fault that creates friction, and then when the um, release of energy is produced, it makes the ground shake. Now we're going to be checking what happens deep inside a fault. You can see both the fault, it's splitting the piece of ground in two. You can see there in the block. Okay, and the fault movement releases the energy as seismic waves radiating from the rupture. So we have where it started or where it's called the focus. It's where it started deep inside the ground. Then you can also check out the epicenter. The epicenter, it's known as the place where it hit first, where it started shaking hardest. Remember that an earthquake, as we are learning that they're due to seismic waves, this energy is released through waves through the earth, and can go as long as many kilometers. So have the epicenter, it's where it started. Okay, it's directly proportional to the focus. So you can see these little lines over here, which means that it's spreading in waves. This is energy being released, and it goes moving everything to its way. We can have different seismic waves. There are four of them. We have the P wave, the S wave, the L wave, which we have two of them, love wave and the Rayleigh wave. Okay, they have different shapes. The P wave is the first one to appear. It's called the primary wave. Okay, and it has compressions and dilations, and it moves straight forward. So it would look like if we are talking about a slinky. And a slinky, you can open it up and close it, and it always goes straight. So that's the primary waves move that way. And then we have the S wave, which is the secondary waves, and the secondary waves move as in a rope that it's been hit up and down. So it sways up and down, making little curves. Okay, and you have there the length of the amplitude and the wavelength. Okay, it depends. As stronger it is, as stronger you can feel it. We also have different waves, which are L waves or loft waves and Rayleigh waves. The loft waves moves side to side. So if you are experimenting an earthquake with a loft wave in it, you will see that it like hits you from side to side. Okay, but the Rayleigh waves will make you jump in your seat. Okay, so it will move up and down. So the earthquakes are measured by a device that is called a seismograph. And this device, it's an instrument used to record the motion of the ground during an earthquake. Okay, there are big ones and smaller ones, but they all have the same science around it. And it's a very simple one. These detect the waves, and they have different kinds, and that's how we know that we have different waves. And then we have them, these seismographic materials, we have them installed all throughout the world under the ground and operated as a part of a seismographic network. So all of them are connected to each other, and then we can get different recordings from different places to check how it's spreading. The earliest of these devices was called a seismoscope because it was rather rudimentary, and it was invented very long time ago. Imagine the year was 132 okay, it was a long way ago, and it was invented by this Chinese philosopher, which was called Chang Heng. And it did not record earthquake. It just indicated that an earthquake occurred, and it showed in which direction it was occurring. So it was made out of a huge vessel, and to the sides it has little balls, okay, on top of it, and depending on the motion that it sensed, the balls came down. So depending on where did the ball come from, it will include that it was from the south, from the east, from the north, or from the west. And the modern seismograph that was developed, it came a long time later in 1890. So we have these machines, and they had told us that earthquakes are not the same. Well, we can feel it. Okay, they have magnitude. That means they're harder or not. Based on these seismograms, we have made different scales. The most known is the Richter scale, which is based on the amplitude of the waves from the epicenter. Then we have other that it's called the body wave, which is similar to the Richter scale, but the Richter scale was simpler and it was widely used. Then we have the surface wave, which are tell you the periods of measured anywhere on the globe, and the seismic moment. And now we are using the moment magnitude. Okay, the Richter scale is no longer in use. Right now, we are using the moment magnitude, which also has a scale from 1 to 10. But it has the measurements of the strength of the earthquake was developed by Charles Richter. That's why it received his name. And the steps, how it works, it measures the interval in seconds from the arrival of the first wave, which was the P, the primary wave, and the S waves, which are the secondary waves. Then it measures the amplitude of the largest S waves, and it uses an estimate to estimate the distance from the earthquake. So at least 3 geographic locations are needed to triangulate this earthquake. But now, like I told you, we are being using the moment of magnitude. Okay, it measures the size of the event in terms of how much energy is released, not just when the waves were received. So it concentrates where the energy is there, and you see the darker points imply that there's more energy released. So in particular, these very large earthquakes have moment magnitude give the most reliable estimate on the earthquake size. And then as a physical quantity, it can tell you how long or the fault has multiplied by the area. So the Earth magnitude also has scales based on the shaking intensity. So it implies the people. So the scale is based on if it was felt or not. So if it was not felt by the people, it's very low, 1. And then if it was felt by all, It's in the scale number 6. And if it was, of course, felt and you can see damage and objects were thrown into the air, is in the scale to 12. So we have seismic hazards. That means that there's probabilities and, of course, dangers to occur. So we can check out and locate where the faults are, like a map that we studied in last class. And we can also learn from what has happened before and assess probabilities. Check them out. Take notes. And of course, estimate their recurrence. Like I said before, history and geology will give you important facts. We know that earthquakes have been cyclic, and if we study historical records and information from the past, we can check that how long they take to occur. This is not exact, but it may give us a quite glance. Then there will when, where they will a next earthquake. We do not know. Science has still not found it because they can tell us probabilities, yes, but prediction, no. They cannot tell us when it is exactly going to happen. But of course, science have been improving and the probabilities have gone up to getting 2 years in advance. But 2 years is a long time. For actually being a quite good prediction, we need to be the 2 days time so that we'll give people time to evacuate and get to safety. So researchers say that right now prediction is impossible. So we have to check an earthquake zone. Okay, so what comes with an earthquake? What happens? First, we can have the shaking, which is the ground motion. Okay, the earth is going to move. Then we have the liquefaction, which is the sand substrates that you have under the ground will get filled with water and they will become liquid or semi-liquid, letting the buildings on top to sink. We will also will have fire and of course destruction that comes with it. And we can also have landslide, which is the slipping of the upper part of the earth, and dam failures, where the water has been stored, and many other problems. We can also have tsunamis, which are seismic Z waves that are produced to the motion produced by the earthquake. So the water comes in as a huge wave and tops on top of the cities. So we can see here a building collapse due to the liquefaction of the land. Okay, you can see that the buildings got into the land, like half of it. They're like sunk in there. And then we also have a lot of problems, which are the most due to the urban fire hazard. Okay, in this case, this example, it's from the San Francisco earthquake back from 1906. And they had, of course, the fires, and the water lines have broken, so they could not get enough water to put the fire out. So the fire consumed almost all the city. We can also have collapses of structures that they just whoops fall down. Not all of it, just pieces. As well, let me tell you this, earthquakes do not kill. Buildings do. Okay? The earthquake produces the shaking. If there's nothing on top of the earth that's been shaking, nothing is going to fall down. But if you are building stuff on top of a probable place or fault, you may get a big hazard of topping out buildings. Okay, over here you can see an example where this school fell on top of itself. It just collapsed. And the people inside, of course, died. And as here you can see that the buildings were torn out, and of course they got on top of the people or other places. But you can see that the problem is because of the quality of the building materials. So we have to be careful. And now we need to improve the codes. Okay, you can see here that just half of this building fell off and the wall collapsed, leaving the rest inside in half. And over down there, you can see that the whole building collapsed. It was standing up straight next to the other ones, but due to the fault on the materials or the building itself, it just went down. So for that, we need to be prepared. First, we need to upgrade the codes, okay? Design codes to improve materials and building strategies. That those are made by our people prepare for that, constructors and engineers. Then you have to strengthen bridges, dams, and of course the lines, the pipelines that are underground so they could resist. Then we have to check out and practice that are called earthquake drills. And we have to make them in our houses as well as in the schools or works or any other place that we may be daily, as well as search and rescue that comes after the earthquake has stopped. Emergency planning also includes having survival kits available and planning evacuation routes in advance. Fire prevention, that way we do not has that big problem. And we have also to need communication alternative as well as education. We need to know what is happening in case to understand it and help ourselves. So we have one of the earthquake response, and it's the DCH. It's called the drop, cover, and hold. And this all goes together. So we first drop where you are onto your knees and hands. And don't wait for it. You feel the shake, you drop. Okay, that way you avoid falling from standing up. Then you have to cover. The first thing that you have to cover is your head and neck. And you cover with your arms while you crawl, okay, until you find a sturdy place like a table or any other shelter that can cover you. If there's no shelter, well, you just stand or crawl next to a main wall. And of course, if you find this shelter, you can hold onto it. That way, if it moves with you. And if you're seated and not be able to drop to the floor, hold your head on neck with both arms and hands. So if you start featuring an earthquake and you can see the earth moving away and cracking into, you can wait for it. Okay, don't panic. That's the first thing you need to do. Stay calm. You've practiced, you know what's happening, you know what to do. Then you go up to drop cover, and hold. So once it's passed, you have to be careful to get away from items that may fall or break. As well, you need to get away from doors. Do not stand next to a door. Once it stops, you need to exit or evacuate using the stairs. Never ever use the elevators. Use the stairs. And finally, you need to get to the emergency assembly point that you have already talked and learned in your area. If you're at your family house, you need to check for the point that you and your family has already set. And if you are at school or at work, you also have to establish that evacuation emergency assembly point. It's where everybody's going to get together. So that's all, folks. So see you later in another class.